In this video, we're going to focus on finding the absolute and the relative maximum and minimum. So let's talk about how it appears on a graph. So let's say if you have a graph that looks like this. According to the extreme value theorem, if we have a function f, if it's continuous on a closed interval from, let's say, a to b, then such a function has an absolute maximum and an absolute minimum. The absolute maximum is the highest point on the graph. So this is the absolute maximum, and this point is the absolute minimum. This point here is a local minimum or a relative minimum, but it's not the absolute minimum. The absolute minimum is the point where the function has the lowest y value. The absolute maximum is the point where the function has the highest y value on that interval. So here we have a local or a relative max at this point. Now let's say if we have a graph that looks something like this. So at this point we have a local minimum. Here this is a local max or a relative maximum. Now even though this appears to be the lowest point of the graph, it's an open circle. And so therefore this is not an absolute minimum. And because the graph goes up forever, there is no absolute max. Now let's say if we had the same graph, but this was a closed circle instead. So at this point, this is the highest point of the graph. So this is the absolute maximum. But it's not a local maximum. Usually the local maximums and minimums occur in the middle of the graph. The function is usually increasing and then it's decreasing. Now what about a function that looks something like this? Identify the points on this graph where it's a local maximum, a local min, absolute max, or absolute min. So here we have a local minimum value. This point is also another local minimum value. And here we have a local or a relative maximum. Now there's no absolute maximum because the graph keeps going upward at both sides. So there's no point which we could say this point is the highest point on the graph. We don't have that. There's no closed circle at the endpoints. So we have a relative max at this point, but it's not an absolute max. However, this point is the lowest of the graph. It's the lowest y value. So we do have an absolute minimum. Now what about this example? Let's say this is a vertical asymptote. So this is neither a local minimum or an absolute minimum. If it's an open circle, then you can't say what the lowest point is. And there's no absolute max or local max. So there's no extrema on this particular graph. Now what about this one? Let's say if we have a closed circle, an open circle, another closed circle, and let's say this is a closed circle as well. So this point is the absolute minimum. It has the lowest y value, but since this is an open circle, this is not an absolute maximum. There's no relative extrema in this particular graph. For you to have a relative extrema, the first derivative must be 0. Typically, you need a shape that looks like this. That's a local max or a local minimum. Now let's talk about those shapes. According to the first derivative test, we can tell if we have a local maximum. Notice that the slope of the function, or the first derivative, is positive on the left side. When the first derivative is positive, the function is increasing. Notice that the graph goes upward on the left side. Then at the top, the tangent line has a slope of 0. So the first derivative is equal to 0 at the local maximum. And then the function is decreasing, so it has a negative slope. So the first derivative is negative. So if the first derivative changes from positive to negative, then you have a local max where the first derivative is 0. So that's the first derivative test. Now here we have a local minimum. And notice that on the left side, the function is decreasing. Whenever the function decreases, the slope is negative, so the first derivative is negative. And then at the local minimum, we have a horizontal tangent line, so the slope is 0, which means f prime is equal to 0. And then on the right side, the function is increasing, so the first derivative is positive. So if the derivative changes from negative to positive as you move from left to right, then at this point, what we have is a local minimum. So that's the main idea behind the first derivative test. The next thing you need to know how to do is how to identify critical numbers. Whenever the first derivative, let's say of c, is equal to 0, or if the derivative, let's say it doesn't exist, then c is a critical number. So if you have a local max or a local minimum, at this point, the tangent line has a slope of 0. So this point is a critical number. Or let's say if you have a function that's continuous, but notice that the slope doesn't exist at this point. It's not differentiable. The slope changes instantaneously. So f prime of c doesn't exist. This point c is still a critical number. Now let's say if we have a function that looks like this. Identify all the extrema on this graph. So here we have a local max, and at this point we have a local or a relative max. At the cusp we have a local minimum, and at this point this is a relative or a local minimum. Now the highest point on the graph is this point, so that's an absolute maximum, but it's not a local maximum. And the lowest point is here, that's an absolute minimum. Now remember, if these were open circles, it would not be an absolute max or min. It has to be a closed circle, and it has to be the highest or the lowest point on the graph. So now let's try some problems. Find the critical numbers of the function and identify all extrema. So let's say the function is f of x is equal to 2x squared minus 6x. And there's no intervals, no closed intervals. So in this case, what you want to do for a problem like this is find the first derivative and set it equal to 0. So the derivative for 2x squared is 4x, and the derivative of 6x is simply 6. So if we set it equal to 0, let's take out a 2. So it's going to be 2x minus 3. And if we set 2x minus 3 equal to 0, we can see that 2x is equal to 3 and x is equal to 3 over 2, which is 1.5. So that's the critical number. C equals 3 over 2. Now what you want to do at this point is you want to plug the number or write it in a number line. Now let's pick a number that's greater than 1.5. Let's say 2. If we plug in 2 into the first derivative, is it going to be positive or negative? 2 times 2 minus 3. 4 minus 3 is a positive number. So it's going to be positive on the right side. And this is the sign of the first derivative. What we're doing here is the first derivative test. Remember, if it changes from positive to negative, then we have a local maximum. If it changes from negative to positive, then the function has a local minimum. So let's pick a number that's less than 1.5. Let's try 1. So if we plug in 1 into this equation, it's going to be 2 times 1 minus 3, which is a negative number. And if you multiply it by 2 on the outside, it's still going to be negative. So we're not concerned about the value. We just want to know if it's positive or negative. So the first derivative is negative when x is less than 3 over 2. So when the derivative is negative, the function is decreasing. And when it's positive, the function is increasing. So therefore, what we have is a local minimum at 3 over 2. So it's located at x equals 3 over 2. Now sometimes you may have a problem that wants you to find the local minimum value. The local minimum value is the y-coordinate of the local minimum. So let's go ahead and find the y-coordinate. So let's plug in 3 over 2 into the equation. So what is 3 over 2 squared? 3 squared is 9, and 2 squared is 4, but I'm going to leave it as 2 times 2. Now 6 times 3 over 2. 6 times 3 is 18. 18 divided by 2 is 9. And here we can cancel one of the 2's. So it's 9 over 2 minus 9. 9 over 2 is 4.5. 4.5 minus 9 is negative 4.5, which is negative 9 over 2. So as an ordered pair, the local minimum exists at this point. So you can say that it's located at an x value of 3 over 2, and the local minimum value is negative 9 over 2. Now, this particular function, does it have an absolute minimum value or an absolute maximum value? How can you tell? Now, if you don't have a closed interval, you need to know the general shape of the function. Since we have a function that's positive x squared, this is the leading term. The general shape for this graph is a parabola that opens upward. So we could see that this function is going to have a local minimum value. But also, notice that the local minimum value is also the absolute minimum value. This is the lowest point of the function. So this point is not only a local minimum value, but an absolute minimum value as well. There's no absolute maximum values because the function will continue to increase towards infinity. So we only have an absolute min, but not an absolute maximum value. Now you want to be familiar with the parent functions of other functions. For example, negative x squared is a parabola that opens in a downward direction. So knowing that tells you that this function not only has a local minimum value, a local maximum value, but it also has an absolute maximum value because this point is the highest point on the graph. Now some other functions that you need to know is y is equal to positive x cubed. This is a cubic function, and this function is always increasing, except at 0. So for this function, there is no absolute minimum value or absolute maximum value. And the same is true for negative x cubed. So if you have a function that has an odd exponent as the leading term, it's not going to have any absolute minimum or absolute maximum values. But if the exponent of the leading term is even, like x squared or x fourth, then it could have an absolute minimum or an absolute maximum value, depending on if it's negative or positive. Another one that you need to know is the absolute value of x. This function is basically a V-shaped graph. So notice that this point is the local minimum, but it's also an absolute minimum. And if there's a negative on the outside, then it opens downward. And so it has an absolute max, and it has a local max at that point. Now, if you see this function, x raised to the 1/3, which is equivalent to the cube root of x, this function does not have an absolute minimum or an absolute maximum function. However, if it's an even function, if it's x to the 2/3, this function is a cusp. It's not differentiable at 0, but it does have a local minimum value at 0 and an absolute minimum value. And if there's a negative in front of it, it's going to open in a downward direction. So it's going to have an absolute maximum value. So pay attention to the type of function that you're dealing with. And so you'll know if it's going to have an absolute minimum or an absolute maximum value. So make sure you know the common parent functions in calculus and the stuff that you've learned in pre-calc. Let's try some more examples. So let's say that f of x is equal to 2x cubed plus 6x squared minus 48x. So go ahead and identify all the extrema in this function and also identify the critical numbers. So the first thing that we need to do is find the first derivative. The derivative of x cubed is 3x squared, and the derivative of x squared is 2x, and the derivative of x is simply 1. So f prime of x is equal to 6x squared plus 12x minus 48. So let's set it equal to 0, and let's find the critical numbers. So we need to factor. Let's remove the GCF. The greatest common factor between 6, 12, and 48 is 6. 6x squared divided by 6 is x squared. 12x divided by 6 is 2x. And negative 48 divided by 6 is negative 8. So now we need to factor this particular trinomial where the leading coefficient is 1. So what two numbers multiply to negative 8 but add to the middle term or the middle coefficient of 2? So it's going to be 4 and negative 2. 4 times negative 2 is negative 8, but 4 plus negative 2 adds up to positive 2. So therefore, to factor it, it's going to be x plus 4 times x minus 2. So the critical numbers are negative 4 and positive 2. To get them, you need to set each factor equal to 0. So if you set x minus 2 equal to 0 and add 2 to both sides, you'll get the critical number x equals 2 or c equals 2. And if you set x plus 4 equal to 0 and subtract 4 by both sides, then x is equal to negative 4. So now let's make some space. Yeah, we don't need this anymore. Our next step is to use the first derivative test. So let's make a sign chart. Let's put the critical numbers on the number line. Now let's pick a number greater than 2. So let's try 3. If we plug in 3 into the first derivative formula, which is this formula, it's easier if you plug it in into the factored version. It makes it easier. If we plug in 3, 3 minus 2 is positive, and 3 plus 4 is positive. So two positive numbers multiplied to each other will give you a positive result. Now let's pick a number between negative 4 and 2. Let's use 0. So 0 minus 2 is negative, and 0 plus 4 is positive. A positive times a negative is equal to a negative number. So if you pick any number between negative 4 and 2, it's going to be negative. Now let's pick a number to the left of negative 4. Let's say negative 5. Negative 5 plus 4 is the negative number, and negative 5 minus 2 is negative. Two negatives make a positive. So now that we've completed the sign chart, let's look at negative 4. At x equals negative 4, do we have a local minimum value or a local maximum value? What would you say? So look at the sign of the first derivative. It changes from positive to negative. So when the first derivative is positive, the function is increasing. So to the left of 4, it's going up. And then when the first derivative is negative, the function is decreasing. So to the right of negative 4, it's going down. So therefore, negative 4 is a local maximum, according to the first derivative test. Now, what about at x equals 2? Is it a local minimum or a local max? So it changes from negative to positive. So when the first derivative is negative, the function is decreasing. And when it's positive, it's increasing. So we have a local minimum value at 2. So now that we know that, we need to find the y values. So let's plug in negative 4 into the original equation and positive 2. So I'm going to use the calculator for this. So at negative 4, the y value is 160. And at 2, it's a negative 56. So we have a local maximum at an x value of negative 4, and the maximum value is 160. Now we have a local minimum, which is located at an x value of 2, which has, and the minimum value is negative 56. So what I want you to understand is that the x coordinate tells you the location of the extrema, and the y coordinate tells you the value of the extrema. So let's say if you have an online assignment and you're asked, where is the local minimum located? The local minimum, or the local extrema, is located at an x value of 2. Now what is the value of the minimum extrema? The value is negative 56. Likewise, the relative maximum is located at an x value of negative 4. And the maximum value of that relative extrema is 160. So the value is the y coordinate and the location is the x coordinate. Now let's try another problem. Let's say if we have an absolute value function. What would you do to find the extrema for this function? Now for an absolute value function, at least one that's simple like this, you really don't need to find the first derivative. You know the general shape of the function. It's going to open upward since it's positive. Now we just need to find the location of the vertex. And all you need to do is set the inside of whatever is inside of the absolute value function, set that equal to 0. And you'll see that x is 2/3. So at 2/3, the function is going to open upward. So therefore, we can see that we have a local minimum value at x equals 2/3, which is also an absolute minimum value. Now, if you want to find the y coordinate, you know it's 0. If you plug in 2/3 into x, the whole thing is going to be 0. 3 times 2/3 is 2. The 3's cancel. 2 minus 2 is 0, so the whole thing is 0. So the absolute minimum value is 0, and it's located at an x value of 2/3. Let's try another example, one that's a little harder this time. So let's say f of x is equal to 5x to the 2/3 plus x raised to the 5/3. So feel free to pause the video and try this example. Go ahead and find all of the extrema and identify the critical points on this particular graph. So the first thing that we need to do is find the first derivative. The derivative of x to the 2/3 using the power rule is 2/3 x to the negative 1/3. After you move the 2/3 to the front, you need to subtract it by 1. 1 is the same as 3/3. So 2 minus 3 is negative 1 with a common denominator of 3. So you get negative 1/3. Now the derivative for x to the 5/3 is going to be 5/3 x, and then subtract 5/3 by 1, which is the same as subtracting it by 3/3. 5 minus 3 is 2, so it's going to be positive 2/3. Now what do you think we need to do at this point? What would you do in order to find the critical numbers? What you want to do at this point is you want to factor the GCF. Now what is the GCF? What is the greatest common factor? Well, let's say if you have 2x squared plus 2 to the x to the third. You would take out 2x squared. That's going to be the GCF. The GCF is the smaller of these two values. 2 is less than 3, so you take out x squared. So if we look at x to the negative 1/3 and 2/3, which one is smaller? Negative 1/3 or 2/3? Negative 1/3 is lower in value than 2/3. So we need to factor out x to the negative 1/3. But we can also take out 5/3 because it's found in both terms. So the GCF is 5/3 x to the negative 1/3. So here we took out a 5, we took out a 3, and we took out this whole thing. So all we have left over is the 2. And now for the next term, we took out the 5/3, but we took out negative 1/3 from 2/3. So then what's going to be on the inside? If you divide 2/3 by x to the negative 1/3, 2/3 minus negative 1/3 is the same as 2/3 plus 1/3, which is 3/3, which gives you 1, or x to the first power. If you distribute it, if you multiply it backwards, x to the negative 1/3 times x to the first power, which is x to the 3/3. Negative 1 plus 3 is 2, so you get 2/3. So it works out. Now the next thing that we need to do is rewrite it as a fraction. We can move this x variable to the bottom since it has a negative exponent. If we do so, the negative exponent is going to change to a positive exponent. So f prime of x is equal to 5 times 2 plus x divided by 3 x raised to the positive 1/3. The 3 was already on the bottom, so we kept it there. So once you have the first derivative in this form, now we could find or write the number line, and we could find the critical numbers as well. So if you have a fraction, here's what you want to do to find the critical numbers. We need to set the whole thing equal to 0. So the critical numbers occur when f prime of x is equal to 0, or when f prime of c doesn't exist. It doesn't exist if the denominator is equal to 0. So that's another critical point. So basically, set the numerator equal to 0 and set the denominator equal to 0, and that will give you the two critical numbers. So if 2 plus x is equal to 0, then x is equal to negative 2. That's the first critical number. So it's differentiable at negative 2. Now we're going to set the bottom part equal to 0. You could ignore the 5 and the 3. because if you put the 3 here, once you divide both sides by 3, 0 over 3 is still 0, so you could ignore these two. So the other critical number is at 0. Now keep in mind, the function is not differentiable at 0. It's continuous at 0. You can plug in 0 into the original equation, but if you plug in 0 into the derivative, it's going to be 1 over 0, which is undefined. So it's continuous at 0, but it's not differentiable at 0, which means that at 0, we have a cusp, something like that looks like this. Now let's make a number line. And let's put the critical numbers, -2 and 0. So now let's test a few points. Let's try 1. 2 plus 1 is positive, and 1 raised to the 1/3 is positive. So to the right of 0, the first derivative is positive. The function is increasing. Now what about between -2 and 0? Let's plug in -1. 2 plus -1 is a positive number. -1 to the 1/3 is a negative number. A positive number divided by a negative number is equal to a negative number. Now if we try a number less than -2, like -3, 2 plus -3 is negative. -3 to the 1/3 is negative. A negative number divided by a negative number is a positive number. So at -2, the function is increasing to the left of -2. The first derivative is positive, so it's increasing, and then it's negative, so it's decreasing. So we have a max at -2. Now at 0, the function to the left of 0 is decreasing, and then to the right of 0 it's increasing. But we know it's a cusp, so it's going to look more like this. It's going to decrease, and then it's going to increase, since it's not differentiable at 0. But we still have a local minimum value. Now you can find the y values if you want to. You know how to do that. So I'm not going to worry about it. If you graph the original function, it's going to look something like this. You can just type in online graphing calculator in Google and type in the function if you don't have a graphing calculator. This is how it looks like if you type it in the graphic calculator. At 0, you can see that we have a cusp, so that is the local minimum value, and at -2 we have a local maximum value. But based on the shape of the graph, there is no absolute minimum or any absolute maximum value. This function continues to increase, so there's no absolute maximum value, and this continues to decrease, so there's no absolute minimum value. Now let's say if you're given the quadratic function 3x squared minus 12x plus 5, and let's say it's on a closed interval 0 to 3. So in this case, how can you determine all of the extrema? Local minimum values, local maximum values, absolute minimum, and absolute maximum values. So we're going to do everything that we did before. We're going to find the first derivative, set it equal to 0, find the critical points, test it on a number line. But in addition to that, we need to make an xy table and compare the y values of the endpoints. So if you're given a closed interval, you need to take that extra step to see if you have any absolute minimum or maximum values. So let's begin. So the first derivative is equal to 6x minus 12. So let's set it equal to 0, and let's take out a 6. So we can see that the critical number is x equals 2. So now let's make a number line. So let's plug in a number to the right of 2. If we plug in 3, 3 minus 2 is positive. And if we plug in 1, 1 minus 2 is negative. So it changes from negative to positive. Therefore, we have a relative minimum. And it makes sense because the leading term is x squared. So therefore, we know we have a parabola that opens in the upward direction. So chances are this is the absolute minimum as well. But let's confirm it. Now that you have the critical numbers, make a table. You want to put the critical number in the table, and you also want to include the endpoints of the intervals. So that's an x value of 0 and 3. So now you want to find the y values at each of these x values. So what is y when x is 0? So it's going to be 3 times 0 squared plus 12 times 0 plus 5, which is simply going to be 5. Now what is y when x is 2? So that's 3 times 2 squared plus 12 times 2 plus 5. So 2 squared is 4 times 3, that's 12. 12 times 2 is 24. 12 plus 24 is 36 plus 5. So that gives us a y value of 41. You know what? I made a mistake. And this is blocking the negative sign. This is negative 12x. So let's put a negative here. So it's going to be 12 minus 24 plus 5. 12 minus 24 is negative 12 plus 5. So that gives us a y value of negative 7. Because we knew that 2 was the local minimum, so it couldn't be 41. That was too high. It has to be a low value. So now let's find the y value for 3. So f of 3 is 3 times 3 squared minus 12 times 3 plus 5. 3 squared is 9 times 3 is 27. 12 times 3 is 36. And 27 minus 36 is negative 9 plus 5 gives us a value of negative 4. So we already know that 2, negative 7 is the local minimum value based on the sign chart. Now notice that 5 is the highest y value. Therefore, this is the absolute maximum. Negative 7 is the lowest y value. So negative 7 is also the absolute minimum, in addition to being the local minimum. Now, if you were to graph the function 3x squared minus 12x plus 5 on your graphing calculator, you should get a function that looks like this. So according to the table, we have the points 0, 5, which is somewhere over here. We also have the point 2, negative 7, and 3, negative 4, which is roughly in this region. So because we have a closed interval, our function should look something like this. But if you type it in the graphing calculator, it's going to look like an upward parabola that's going to extend in the upward direction. But this is the graph that we have because it's restricted on the interval from 0 to 3. So therefore, for our graph, we could see that the absolute maximum is this point, 0, 5. It's located at an x value of 0, but it has a maximum value of 5. The function has a minimum value of negative 7. So this is the absolute minimum value, and it's located at x equals negative 2. And as we can see, it's also the local minimum value, because at this point, the first derivative is equal to 0. The slope of the tangent line is 0. For the sake of practice, let's try another example. F of x is equal to 2x to the fourth minus 4x squared minus 1. So go ahead and try this one on the interval -2, 3. So just like before, the first thing we're going to do is we're going to find the first derivative. The derivative of 2x to the fourth is 8x cubed, and the derivative of 4x squared is 8x. The derivative of a constant is 0. Now we need to set the derivative function equal to 0, and let's solve for x. So let's take out the GCF, the greatest common factor. So 8x cubed divided by 8x, that's x squared. And negative 8x divided by 8x is negative 1. Now we can also factor x squared minus 1. Using the difference of square methods, it's going to be x plus 1 times x minus 1. So now, let's draw the number line. So there's 3 critical points, -1, 0, and 1. So for x minus 1, it's going to be positive 1. For this one, it's negative 1. And also, you could set 8x equal to 0, which means that x is 0. So those are the 3 critical numbers that we have for the first derivative. Now, let's determine the signs. If we plug in a number greater than 1, let's say 2, 2 minus 1 is positive, 2 plus 1 is positive, 8 times 2 is a positive number, so everything is going to be positive. Now, if the multiplicity of each 0, if it's odd, is simply going to change sign. So this is going to be negative, positive, negative. It's going to change across each critical number. For example, if we plug in 0.5, 0.5 minus 1 is negative, 0.5 plus 1 is positive, 8 times 0.5, that's positive. So overall, it's a negative. If we plug in negative 0.5, negative 0.5 minus 1 is negative, negative 0.5 plus 1, that's positive, and 8 times negative 0.5 is negative. So it's a negative times a positive times a negative, which overall is a positive number. Now at -1, the function decreases and then it increases. So we have a minimum value at -1. At 0, notice that it increased then decreased. So we have a local max at 0. And then at 1, it decreases then it increases. So we have a minimum at 1. So now let's make a table. So we need all the critical numbers, -1, 0, and 1, in addition to the endpoints, -2 and 3. Now let's find the y value for each of these x values, and let's see which one is going to be the minimum and which one is going to be the maximum. So we know that 0 is the local max, and -1 and 1 represent the local or relative minimum values. So now we got to see which one is the absolute extrema. So let's plug in 0. If we plug in 0 into the function, the y value is going to be -1. If we plug in 1, it's 2 times 1 to the fourth minus 4 times 1 squared minus 1. So that's 2 minus 4 minus 1. 2 minus 4 is -2 minus 1. That's equal to -3. If we plug in -1, notice that we'll get the same answer. This is going to be 2. -1 squared is 1, so this is -4. And so overall, it's still going to be -3. Now let's plug in -2. Negative 2 to the fourth power, that's 16 times 2, that's 32. 2 squared is 4 times negative 4, that's negative 16. 32 minus 16 is 16 minus 1, that's going to be 15 overall. And at 3, it's going to be 2 times 3 to the fourth minus 4 times 3 squared minus 1. 3 to the fourth is 81 times 2, that's 162. 3 squared is 9 times 4, that's 36. And 162 minus 36, that's 126 minus 1. So you get a value of 125. So we can clearly see that 125 is the absolute maximum value. In addition, we can see that negative 3 is the absolute minimum value. So both of these values are absolute minimum values. Negative 3 is the lowest y value in this interval. Now let's graph the function. So we have a local max at 0, negative 1, and 2 local minimum values at negative 1, negative 3, and 1, negative 3. And we have an endpoint at negative 2, 15. So let's say this is 15. And another one at 3, 125. So let's say this is 125. So the graph looks like this on the restricted interval. Now if you plot it on a graphing calculator, this function will continue to increase. However, on a restricted interval, it looks just like this. So you can see that these 2 points are the absolute minimum points in addition to being the relative minimum points. And here we have a local max. And this is the highest point on the graph, so this is the absolute maximum value. So now that you understand the process for finding the absolute extrema on a graph, let's focus on harder problems now. So let's say if we have the function f of x is equal to x divided by x squared plus 1 over 5. And let's say it's on the interval negative 1 to 2. So go ahead and identify all of the extreme values in this function. So to find the first derivative, we need to use the quotient rule. So let's say if this is, let's call the top function u and the bottom part v. So if you differentiate u divided by v, it's going to be vu prime minus uv prime over v squared. So v is x squared plus 1 over 5 times u prime, the derivative of x, that's 1, minus u, which is x, times v prime. The derivative of x squared plus 1 over 5 is simply 2x, and then divided by v squared, which is x squared plus 1 over 5 squared. So that's the first derivative. Now let's simplify what we have in the numerator. So x squared plus 1 over 5 times 1 is simply x squared plus 1/5, and then minus 2x squared, divided by what we have in the bottom. So x squared minus 2x squared that's going to be negative x squared divided by x squared plus 1/5 squared. So that's the first derivative. Now what can we do to find the critical points? Since we have a fraction, we need to set the numerator and the denominator equal to 0. So let's start with the numerator. 1/5 minus x squared. We can add x squared to both sides, and then we can take the square root of both sides. The square root of 1 is simply 1, and then on the bottom we have root 5, plus or minus. Now if we set the denominator equal to 0, if we take the square root of both sides, we're going to have x squared plus 1/5 is equal to 0. Now if you subtract both sides by 1/5, x squared cannot equal negative 1/5. So therefore, we're not going to get any critical numbers from the denominator. So the only critical numbers that we have is 1 over square root 5, which as a decimal, that's 0.447. So I'm going to round that and say it's 0.45. So now let's plot the critical numbers on a number line. So the first one is at negative 1 over root 5, and the second one is positive 1 over root 5. So now let's plug in a few test points. So let's pick a number greater than positive 0.45. So let's plug in 1. 1/5 minus 1 squared is a negative number. 1/5 is 0.2. 0.2 minus 1 is negative. The bottom part will always be positive because it's squared. So we don't have to look at the denominator. It's always going to be positive. Now let's say if we pick a number between negative 1 over root 5 and positive 1 over root 5. So let's try 0. 1/5. Oh wait. This should be negative overall. We said the bottom is positive, but 1/5 minus 1, that's a negative number. So overall, it's negative past positive 0.45. Now, let's say if we pick 0, which is between these two values. 1/5 minus 0 squared is simply a positive number. Now, if we pick a number less than negative 0.45, let's say negative 1, negative 1 squared is still 1, so it's 1/5 minus 1, which is negative 0.8, and that's a negative number. So it changes from negative to positive, so that's a minimum, and then positive to negative, so we have a local max at positive 0.45. So now what we need to do is make a table. So we're going to use the points negative 1, negative 1 over root 5, 1 over root 5, and 2. So we said that negative 1 over root 5 is a local minimum, and positive 1 over root 5 is a maximum. So let's get rid of this stuff. So let's start with negative 1. If we plug it into the function, it's going to be negative 1 over negative 1 squared plus 1/5. So negative 1 squared is 1. 1 plus 1/5, that's 6/5. 1 is basically 5/5, and 5/5 plus 1/5 is 6/5. So 1 over 6/5 is basically 5/6. And let's get the decimal value for that. So negative 5 over 6 is about negative 0.83. So now let's plug in the next value, negative 1 over root 5. After you square negative 1 over root 5, it's going to be 1 over 5. So what we have is negative 1 over root 5 divided by 2 over 5, which at this point, it might be wise to just type this in a calculator. So the exact value is negative root 5 over 2, but as a decimal, it's about negative 1.12. Now this number is going to be the same, but it's going to be positive. It's positive 1.12. After you square it, this is going to be positive, but here it's not going to be negative, it's going to be positive. Now let's plug in 2 into the equation. So it's going to be 2 over 2 squared, which is 4, plus 1 over 5. 1/5 is about 0.2, so this is 2 over 4.2, which is very close to a half. So it's about 0.48. Now let's analyze what we have. So the lowest y value is negative 1.12. So therefore, not only is this the local minimum, but it's also the absolute minimum as well. Now the highest y value is 1.12. So in addition to being the local maximum, it's also the absolute maximum. Now if you were to draw a graph, if you were to sketch it, it looks something like this. Initially it decreases, and then it increases, and then it decreases again. So here's the local max at 1 over root 5, and here's the local min at negative 1 over root 5. Try this one. Let's say if f of x is equal to x times square root 9 minus x squared. And let's say it's on the interval negative 2 to 3. So what can we do to find the first derivative? We need to use the product rule. So let's say if you have two functions, f times g. According to the product rule, it's going to be f prime g plus f g prime. So if f is x, and if g is 9 minus x squared raised to the 1/2, then f prime is 1. G is still the square root of 9 minus x squared. F is x, but g prime is 1/2 9 minus x squared to the negative half times the derivative of the inside, which is negative 2x. So let's simplify what we have there. So it's the square root of 9 minus x squared. 1/2 and 2 cancels, and then it's negative x squared, which is x times negative x. And notice that the 9 minus x squared is raised to the negative 1/2. So let's bring it back to the bottom, which the negative exponent will now be positive. So instead of writing it as 9 minus x squared raised to the 1/2, we can simply write it as the square root of 9 minus x squared. Now at this point, you don't want to set the first derivative equal to 0 just yet. You still need to do some work here. You want to combine it into a single fraction. So let's multiply this expression by the square root of 9 minus x squared over 9 minus x squared. So root 9 minus x squared times root 9 minus x squared is simply just 9 minus x squared, divided by 1 times this That's going to be the square root of 9 minus x squared. So now that we have common denominators, we can combine the numerators. So 9 minus x squared is equal to 9 minus 2x squared divided by the square root of 9 minus x squared. So this is the first derivative. And now at this point, we want to set it equal to 0. So to find the critical numbers, set the numerator and the denominator equal to 0 separately. So let's start with the numerator. So if 9 minus x squared is equal to 0, we can add 2x squared to both sides. So 9 equals 2x squared. And then we could divide by 2 and then take the square root of both sides. The square root of 9 is 3. So it's 3 over root 2. You can rationalize it if you want, but I'm going to leave it like this. And it's going to be plus or minus. Now, for the denominator, don't worry about the square root. Set the inside part equal to 0. If you set the whole thing equal to 0, once you square both sides, it's going to work out to be 9 minus x squared is equal to 0. The 0 squared is 0. And the square of a square root will simply cancel. So now if we add x squared to both sides, 9 equals x squared. If we take the square root, then we can see that x is equal to plus or minus 3. So now let's make a number line. So we have 3, negative 3. 3 divided by the square root of 2 is about 2.12. So we have 3 over root 2 and negative 3 over root 2. Now we don't need to plug in anything past 3 because the interval stops at 3. And if you plug in anything past 3, it won't be defined because you'll have a negative inside the square root. So the domain of this function is restricted from negative 3 to 3. Plus we have this that restriction. So let's plug in a number between 2.12 and 3. So let's try 2.5. 9 minus 2.5 squared, that's going to be a positive number. But if we plug in 2.5 squared into the top, that's negative 3.5. So it's negative. And if you plug in, let's say, negative 2.5, because this is squared, it's going to give you the same result. But if you plug in 0, a number between negative 3 root 2 and positive 3 root 2, then it's going to be positive. 9 minus 2 times 0 squared is simply 9, so it's positive in this region. So it decreases then increases, so we have a minimum value at negative 3 over root 2, and then it increases then decreases, so this is a local max. Now we can make the table. So we need to choose negative 2, the endpoint, and the other endpoint of 3. And then these two values. Negative 3 is outside of this interval, so we don't have to worry about it. So now we just need the original function. So let's start with negative 2. So it's negative 2 times the square root of 9 minus negative 2 squared. Negative 2 times negative 2 is 4. So this is 9 minus 4. So this is negative 2 square root 5. That's the exact value. But as a decimal, it's about negative 4.5 or negative 4.47. Let's plug in 3. 3 squared is 9, and 9 minus 9 is 0. So the whole thing is 0. Now let's plug in positive 3 over root 2. So this is 3 over square root 2, and then 9 minus 3 over root 2 squared. 3 squared is 9, and root 2 squared is just 2, since root 2 times root 2 is the square root of 4, which is 2. So this is 9 over 2. 9 over 2 is 4.5. So 9 minus 4.5 is 4.5. So this is the square root of 9 over 2. And the square root of 9 is 3, divided by the square root of 2. 3 times 3 is 9. Square root 2 times square root 2 is 2. So the whole thing is just 9 over 2, or positive 4.5. Now what about negative 3 over root 2? Well, it's going to be the exact same thing, but there's just going to be a negative sign on the outside. If you plug in negative 3 over root 2, once you square it, it's going to be 9 over 2. Plus you have this negative on the outside. So the whole thing is just going to be negative 4.5. So in this interval, we could see that the absolute max occurs at this point, and the absolute min is negative 3 over root 2. The graph looks like this. If you were to plot it in a graphing calculator, starting from negative 3 to 3, initially it decreases, then it increases, and then it decreases. So this is negative 4.5, and this is 4.5. So you can see that this is the absolute max, and here's the absolute min. Now at negative 2, that's where we have the endpoint, which is just above negative 4.5, and that's negative 4.47. So we really need to take away this portion of the graph, because it starts at negative 2 and it ends at 3. Now we need to be very careful about something. So this point is the local minimum and the absolute minimum from the interval on negative 3 to 3. But here's a question for you. This point, negative 3 over root 2, is it in this restricted interval? If it is, then that means that this indeed is the absolute minimum. But if it's not, then we have to remove it. So let's find the decimal value of 3 over root 2. 3 divided by the square root of 2 is 2.12. So particularly, this is negative 2.12, which is not in the interval. So you got to watch out for that. So that means we need to remove this point. So even though it would be the local minimum value, because it's not in the interval, we can't use it at all. So therefore, we need to take away the left side of the graph. So negative 2 becomes the absolute minimum value. Because if this graph is not there, negative 4.47 is the lowest y value compared to 4.5 and 0. So this is the true absolute minimum value in this interval. But 3 over root 2, that's still the absolute maximum value. And it's also the local max as well. So make sure that the points that you use is in the interval.